Welcome to Introduction to Analytical Separations. We're going to look at Introduction to Separation Science. To start with, what is separation science? Generally, we'll call it a collection of techniques for separating complex. So what is separation of analytes? Separation are key aspects of many modern analytical methods. Analytical techniques. Real-world samples contain many analytes until combined with. And many analytical methods do not offer sufficient basic types of separations to be able to separate all the analytes that might be present. So most separation method involves chromatography, the analyte into distinct chemicals. We can have liquid solid chromatography. So basic types of separations. Exchange chromatography. We can have separation method based on rate processes. So we can have barrier separation and gas solid, where we have membrane filtration dialysis, electrodialysis, electroosmosis, reverse osmosis, Russian chemists and botanists. Then you can have Michael Swelt, where we have electrophoresis, coined the term chromatography, centrifugation. So chromatography was first major separation science. So chromatography was rediscovered by work on separation of plant pigments when it published its analytical significance about appreciated 1903. And then it gained, actually Kohn received so the IUPAC Nobel Prize in Chemistry in 1937. Chromatography is a physical method of separation carotenoids in which the components to be separated are distributed between two phases. One which is stationary, while the other moves. Stationary phase is held in a narrow tube. So stationary phase, mobile phase, is a common name for under pressure. The column often a porous, high surface area substance. Now you can see how separation is. Here we have, for example, liquid chromatography is done. The mobile phase is liquid solvent, where we have our sample being introduced at this particular end, where mobile phase you find that the sample contains A and B. And this we have some terms here, like retention time. Then it is a way moving to characterize chromatographic retention. You can see that, and is to measure the time between the injection and the time and the maximum of the detector response for the analyte. And those two factors, which is usually called you will see them time, so much is inversely proportional to the element flow rate and gas chromatography. So then there is what we call retention volume. This is now the product of the retention time, and the effluent you can be able to see is called the retention volume. Retention type and so this is a then we have liquid chromatography chromatogram. That time, and then the detector here is peak width at base. UVs. So detector piece in separation science. Generally we expect that we are going to have a Gaussian, but in reality we will always find that you will realize that either tailing peaks or fronting peaks. So that is the retention and differential migration in chromatography. The reason why we are having those particular anomalies. So then here you find that mobile phase velocity and flow rate substance, the average linear phase velocity of this particular one prefers mobile phase through a column is obtained by dividing the length of the relationship between retention time and distribution constant. So you can be able to see the velocity. You will realize that we have length of column divided. You can realize the example here. So then we have retention factor. This leads to the retention K as a retention factor solute. So and we will derive that equation to a point where now we have the formulas. So K So relative migration rate, what we call the selectivity factor. Now it gives us a very simple selectivity factor, the ability of a given stationary phase to the retention factor K is used to compare migration. So there is what we call band broadening factor or column efficiency. By definition, after injection, a narrow chromatographic band, the numerator is always larger than the denominator during its movement through the column. The higher the separation efficiency and peak width, the smaller the number of components. The peak width can be separated in a given is an indication of peak sharpness. So the sharpness of the peak in general is an indication of the column efficiency. However, the peak width is dependent on theoretical parameters. One is column length, and another one is step flow rate between the analytical size, mobile phase. So in absence of a specific and this is just calculating theoretical plates. Ideally a plate, something physical, but today is to describe the efficiency of a chromatographic column. So a number of theoretical plates, plate number, the number of plates. So in practice, band broadening processes is convenient to measure. As you can see, this one either at the base and that baseline or at the non-column broadening, dispersion of analyte in a dead volume of an injector, volume between injector. So column band broadening originates from three main sources and detector. Multiple paths of an analyte broadening through the column packing, molecular diffusion, effect of mass transfer. So you can be able to see relationship between plate. So in 1956, J.J. Van Dimter. So the Van Dimter equation is made to introduce the first equation, which combined all three sources. See here. So at this point is where we have minimum velocity. The eddy diffusion, molecules may travel unequal distances in a packed column bed. So as you can be able to see, the red one and the so the first cause of band broadening is differing flow velocities if present through the packed column cause eddies. This may be written as so air depends on so in this equation, then Van Dimter B term is the plate height arising from the longitudinal diffusion. So the concentration of analyte velocity is less at so the dp is the average particle diameter than at the center. Then so the Van Dimter diffuses out. The longitudinal diffusion along the column long axis leads to band broadening high the chromatographic zone, or the diffusion. This process may be described by the equation as you provided there. So then we have lastly Van Dimter C term, resistant to mass transfer. Is the analyte diffusion. So the analyte takes a certain amount of time to equilibrate between the stationary symbol here phase and the mobile phase. So if the velocity of the mobile phase is high, so the slower has a stronger affinity, the more for the stationary phase, then the analyte in the mobile phase inside the particle, and the less then the Van Dimter equation, when you bring all those three terms together, so on the other hand, unified at the faster flow rate. So the most significant result is that there is an optimum eluent flow rate where the separation efficiency will be the best, and it is similar for many compounds. So that is the most important thing to get. So improving resolution, for good resolution in separation, the three terms can be optimized. So increasing retention factor, one you can do is change temperature. Thank you for chromatography, and also change mobile phase class composition. More studies can be done on a school. Increasing number of plates. Thank you.